Hi, I am Evripidis Christodoulides and my project is identifying players in broadcast sports videos, supervised by Dr. Aphrodite Galata. It focuses on the problem of automatic tracking and identification of players in broadcast sports videos shot with a moving camera from a medium distance. Labeled tracks will allow for automatic generation of game and player statistics and video streams that highlight particular players. Player identification is challenging in such videos due to blurry facial features and rarely visible player numbers, and so this simplified dataset containing 4 football players is evaluated with the intention to test on real broadcast sports videos in the future. This video is taken from a static camera, but the project development works equally well when the camera is moving. The project consists of 3 main components: a player detection system, a player identification system, and a player tracking system. Before the main development, I had to collect the training data. For this particular video, because the camera is static, the only pixel values that are changing in each frame are the pixel values of the players as they are moving. So, if we take an image of the background, subtract it from each frame, and then threshold the difference image, we will end up with a binary image, with the white pixels having a value above the threshold. After obtaining the binary image, I joined all the continuous points along a boundary that have the same intensity. For each closed curve that was created, I drew a box and I removed the boxes that were not of desirable size. Finally, I drew the boxes on the original video and stored them as training data. The first main component is player detection. Firstly, I identify the pitch and then player detection is performed only in that area, so that I am detecting only the players and not anyone else like the crowd. Since the pitch pixel values are almost the same, I set lower and upper bounds for the green color of the pitch, and then for each frame I find the pixels that are in that range. The results are mostly the pixels of the pitch, and then with a symbol algorithm I can locate the pitch in each frame. For the actual player detection, I used the histogram of oriented gradients feature descriptor. The technique calculates the gradient magnitude and gradient direction of all pixels in an image and then computes a histogram of gradients for localized portions of the image. The histograms are then normalized so that they are not affected by lighting variations and concatenated to create one single vector representing the image. Histogram of oriented gradients are computed for all training images and then used to train a support vector machine to determine which images represent players. Then a window is scanned across the pitch in each frame to find the locations of the players. The pitch is also scanned at different scales, and with this way it can deal with zooming cameras as well. This is the result after performing this process on the video. While each detection may in fact be valid, we certainly don't want more than one box on top of each player. To fix this, non-maximum suppression algorithm can be used, which removes the box with the lowest probability of being a detection if the intersection area of 2 boxes is greater than 1/3 of the box. This approach seems to work correctly at first glance. However, it doesn't do well with players near each other and occlusions. Although the algorithm is able to detect both players, the box of the one is removed by the non-maximum suppression algorithm. Since sports videos have lots of occlusions and players near each other, we definitely don't want this, and so another approach is going to be used, which I will describe later in the video. The second component is player identification. For player identification, I'm using a combination of shift and MSCR feature descriptors. The shift algorithm detects and describes local features in images that are invariant to scale, rotation, illumination changes, and small viewpoint changes. This makes them a good selection for identifying sport players. The MSCR algorithm detects regions in images whose intensity values are different to that of their surroundings. Multiple thresholds are applied to the image, and areas that remain visible after each threshold are considered. Then the following process is carried out for the shift and MSCR features separately. For each training image, I detected features and extracted descriptors to build a visual dictionary. Next, I clustered the descriptors using the K-means algorithm. The centers of the clusters are used as the visual dictionary's vocabularies. Finally, for each training image, I made a histogram from the frequency of the vocabularies in the image. These histograms are known as the bag of visual words and are used to train a k-nearest neighbor classifier for performing the final classification. For each testing image, I am detecting features, extracting descriptors, and clustering the descriptors. I am then building a histogram from the frequency of the vocabularies in the image, and the k-nearest neighbor classifier is used to compute the image's nearest neighbors. The most common label of the neighbors is assigned as the identity of the image. So the approach I used is to classify all the detected boxes and then use non-maximum suppression on the boxes of each player separately. With this way, we do very well with players near each other and occlusions, but we have some false positives as shown because not all the boxes on top of a player are classified correctly. However, this is not a problem because we can deal with it in the final project component. The final component is player tracking. A tracklet is created for each player, which stores the player's locations at subsequent frames along with the classification results from the identification classifier. Then, for each new frame, I find the smallest distance between any tracklet's last location and any new detection and assign that detection to that tracklet. This process is continued with the remaining tracklets and remaining new detections until all tracklets are assigned a new detection or no new detection is available. While performing this process, two things must be considered. The first is temporal coherence. Players are expected to be close to their location in the previous frame, so a threshold is set and the tracklets are assigned only detections that are close. Secondly, if the tracklet has not been assigned a new detection for a specified number of frames, then the tracklet is restarted. This happens in case a false detection is assigned to a tracklet. A conditional random field is then constructed for each tracklet to perform probabilistic inference about the player identities and help with ambiguous classifications. The Y nodes represent the identity for detection at time t, and the X nodes represent the local evidence terms that are computed by the identification classifier. The conditional random field is then used to predict the most probable sequence of labels, and the most common label is assigned as the identity of the tracklet. I evaluated the system trying different combinations of parameters. The best detection precision and recall achieved was 94% and 99% respectively, and the best identification accuracy achieved was 79%. I then evaluated the whole system together with the detection precision and recall and identification accuracy being 100%. The results are promising to test on real broadcast sports videos. Future improvement can be done for the identification since the accuracy is 79% and the conditional random field is doing a good job helping with ambiguous classifications.